All right, let's go ahead and get started. Today we are going to be working on Newton's law of cooling and the like, and finishing up section 3.4 and then moving on into section 3.5. So I got a couple of things to mention to you guys on that. So let me come over here to our Canvas site. And you'll notice how many sections are in chapter 3. We all go all the way up 3.7, but we actually omit 3.6. So we're doing finishing up 3.4 today, moving on into 3.5. And therefore, we'll be going in after 3.5, moving into 3.7, and that means, test number 3. So I've already posted over here. Here's your link to your homework number 3, test 3 review. And also, just like before, and this thing is going to be due on Thursday, which is, was it March 29th, I believe it is. We'll double check that. I probably should put that on there. Thursday, due by Thursday, and then I didn't put the date on it. I shall fix that. Tell you what, I'll fix it now. Edit, no time like the present. Come over here. That was due by Thursday, comma, March 29th, if memory serves. Come over here, let's see here. Yes, that would be March 29th. And I will save that. At the beginning of class, you are to submit your answers just like before on Canvas. All your answers are going to be on Canvas under the little link under the homework set thing there. And I will show you where that's at. And you're to turn in the free response part of the homework set and stuff, and for a grade. And it will be due on Thursday's class. You know, when is it usually due for us? Friday. But there's a problem. Friday is actually Good Friday, and there's no school on that Friday, the 30th. So I have to make it actually due in class that particular day. So I'll let you know. But don't worry, I will still post a video for you guys of me actually going over the solutions and stuff. That being said, just to hit your modules and stuff, and just like before, you just turn in the free response part, but you actually do the entire homework set and submit your grades on Canvas through the little link here. So let me scroll down here. 3.7. See, we go from 3.5 to 3.7. And then here is your test review, and it's already up and active. So click it right here. It's due on the 29th. There it is. That Thursday, and you can go ahead and I preview the quiz. You actually take the quiz. So there you go. And you will answer all the questions, but just the free response part of the questions, you'll turn in this thing on that particular Thursday and stuff. So just like before. So, and which means also, if that is the case, if we have the test on, the homework set due that Thursday, what does that mean about your test? Big red there. It also means your test 3 will be on Tuesday, April 3rd, 2018. So, okay, go ahead and get you guys set up. Also, a lot of people were complaining about this weird trig review thing, that things weren't matching up and stuff like that. Well, hopefully I fixed that. So, some professor came by and messed up the system, so I had to go back and fix the system. So, in section 3.5, we're going to be going back over some trig, and there's a special trig review, and I'm making that due on March 22nd. That will actually match up to what's on Canvas, hopefully. What's on WebWork, that is. So everything else should be actually fixed in terms of the dates and stuff like that. Okay? So let you guys know. Alrighty. So let's get back to where we were ended up. So lots of announcements today. Katrina is actually passing back a special assignment that was not in your notes. We're going to look at this in just a second. But before we do that, I wanted to actually talk about this particular problem here, Newton's law of cooling. And we talked a little bit about it last time. You know, and in the applications of this stuff. So we make up an interesting problem here, but I try to give you guys more real-world problems of where this stuff's actually used at and stuff. So, here we go. This is a Newton's law of cooling problem, and I'll dive into this a little bit deeper in just a second. But it says this. A roasted turkey is taken out of an oven when its temperature has reached 175 degrees Fahrenheit. and is placed on a table in a room where the temperature is 65 degrees Fahrenheit. If the temperature of the turkey is 155 degrees Fahrenheit after half an hour, what's the temperature after 45 minutes? All right, when it comes to the Newton's law of cooling, this is your, basically your big formula, but this is the traditional formula that I use, which is C e to the KT plus TS, where C is an initial temperature, surrounding temperature. You'll actually find that it's T0 minus TS is what it actually is, e to the KT. So it's still an exponential function type thing here, but TS is your surrounding temperature. So I got this thing coded T, big T of little t. Big T is temperature, little t is time. Temperature after time T. TS is the surrounding temperature. C is the initial temperature minus the surrounding temperature. K is your growth or decay constant, depending on, and I talk about a growth or decay constant because it depends. If I pull a turkey out of the oven and put it in room temperature, what is the temperature of the turkey going to do? It's going to move towards room temperature, right? So in that case, it would be going down. If I take an ice cream out of the freezer and just sit it there and watch my kids just stare at it like dogs dripping from the mouth there, if they got doing that, what's going to happen to the ice cream if I'm just going to be mean and not allowing them to have it? They just have to stare at it. What's going to happen to the ice cream? It's going to move towards room temperature and go from cold to hot, so that actually would grow. Does that make sense? So depending on the direction that your temperature is going, whether K is going to be positive or negative. All right, and obviously that's supposed to be a little t. This is a little t, and that's supposed to be time. So, as you read these problems, let's pull this thing off. A roast turkey is taken from an oven when the temperature has reached 175 degrees Fahrenheit. That is my initial temperature. T of 0 is 175 degrees. Okay? And is placed on a table where the room temperature, that would be the surrounding temperature, is 65 degrees Fahrenheit. If the temperature of the turkey is 155 degrees Fahrenheit after a half an hour, what's the temperature after 45 minutes? You got a problem. And this is the kind of problem you need to pay attention to. This is classic physics. You got to pay attention to your units. So they're talking two sides of their mouth on this one. They're talking about a half an hour, and the next thing they're talking about is 45 minutes. Those aren't the same units. Yes, they're time units, but they're not the same units. So you've got to decide right from the beginning, do you want this problem to be in minutes, or do you want it to be in hours? It's your choice. But how you direct it will make how the numbers actually work out for you. You'll still get the right answer at the end of the day, but you'll have to figure out what kind of units you want to use. You want to convert everything to minutes, you want to convert everything to hours. Your choice. What would you do? You want to go minutes? Fine, we'll do minutes then. So you guys decided on minutes. So that tells me the temperature after a half an hour, that's 30 minutes. You with me? So temperature after 30 minutes is equal to 155 degrees Fahrenheit. The question is, what is the temperature after time equals 45 minutes? Okay? Now look at this formula. Big T of little t is equal to C e to the KT plus TS. In this problem, we know what TS is. What is our surrounding temperature? 65 degrees. That is a fixed constant that goes right in here. So I got the formula. Big T of little t equals C e to the KT plus the surrounding temperature of 65 degrees. Okay? If you look at this formula, you will notice there are two constants we don't know. The big C out front and the K, which is your decay or growth constant, depending on the situation here. Does that make sense? That is why these two constants here with the surrounding temperature, that is why you actually have to have two actual measurements of whatever you're analyzing, whether it be the turkey or ice cream or the O.J. Simpson problem we'll do in a minute. Okay, you have to actually have measurements, two different measurements of the body that you are actually working with. The first measurement was this. T of 0 equals 175. This was the initial temperature when you measured the bird. It came right out of the oven. It was 175 degrees. We took the little thermometer, stuck it in there, and the little bird, you know, you seen your mom do that in the kitchen and stuff, and pull it out on the stove. The bird's 175 degrees, it's ready to eat, right? It's hot, but it's ready to eat. So, here we go. T of 0 is equal to C e to the k times time is 0 plus 65. The reason why you want to use this initial temperature first is because what's k times 0? 0, and e to the 0 makes it 1. So this thing goes away, so it's 1. And by the way, that T of 0 equals, what was it, 175. So I got C times 1 plus 65 equals 175. So when I solve for C, it's 175 minus 65. That is why, if you put up here in the formula, that C is actually equal to T0, the initial temperature of the whatever you're playing with, minus the surrounding temperature. That's exactly what I'm doing here, which is equal to, I don't think I need a calculator for that, 110. You with me? Which means my formula is big T of little t is equal to 110 e to the kt plus 65. We're on our way and working here. The goal is to get this mathematical formula, the modeling equation. Now I need to solve for k, but I had to find that big C first, and I did that actually through the initial temperature. Now, I'm going to use this particular information here. After 30 minutes, the bird was 155 degrees. So T of, you decided on minutes here, 30 minutes, equals 110 e to the k times 30 plus 65, and that will be equal to 155. Now you got your equation. All right. I did all that, grabbed all those papers, and the one thing I forgot is a calculator. Can I borrow somebody's calculator today? Thank you. I will return it. I don't care what you hear. All right. So, here we go. What am I going to do? Solving this equation here. First thing I want to do is I got to get the e with the the k, which is what I'm trying to solve for, is that k by himself. So what's my first move? I'm going to subtract 65 from both sides. So that gives me 110 e to the 30k is equal to 155 minus 65. Should be 90. Yeah, okay, I can do that kind of math. 90. And now what's my next move? Divide by 110. I got to get that e by himself. So I get e to the 30k equals 9/11ths because the zeros cancel there. And then what's my next move? The big move on solving for the exponent of an e. What am I going to do? Take the natural log of both sides. This cancels and leaves me with 30k is equal to the natural log of 9/11ths. Okay? I'll blow it up for you guys in the back there. And then the last move is divide by 30. And I get k to be equal to the natural log of 9 divided by 11. That closed parentheses divided by 30. And because the bird is hot coming into a colder room, the temperature is going down, so I am expecting a negative k constant here. This would be negative 0.0066890232. And remember, this is math. We don't round, we use all the decimals. Okay? Does that make sense? So therefore, my modeling equation is the temperature of the turkey is equal to 110 e to the k, which is negative 0.0066890232 t plus 65. This is the formula that's going to model the temperature of the turkey. Does that make sense? Now, what was the question? Oh, yeah. What is the turkey, or what's the temperature of the turkey after 45 minutes? What am I going to do to this problem? Plug in 45. So the answer to the question, T of 45 is equal to 110 e to the negative 0.0066890232 times 45 plus 65 equals, and I'm just going to stick this on the calculator, 110 e raised to the negative 0.006 6890232 times 45 plus 65, and I get 146.408063 degrees Fahrenheit. So after the bird is sitting there cooling on the kitchen table there, after 45 minutes, the bird is now 145 degrees. That's that center temperature. Does that make sense? Did I lose you guys anywhere? When will the turkey have cooled to 110 degrees Fahrenheit for that central temperature? 110 degrees. By then we can put it into the refrigerator or something. Or why 110? I don't know. But okay, we're going to find when. When is a question of what? Time. We want to figure out time. So I got my equation again. Big T of little t is equal to 110 e to the negative 0.0066890232 t plus 65. And we want to figure out when that's equal to 110. Solving for time. So my first move is I'm going to subtract 65 from both sides. That gives me 110 e to the negative 0.0066890232 t equals 110 minus 65 is 45. My next move, divide by 110. This gives me e to the negative 0.0066890232 t equals 45 1/10. Now what's my next move? To get rid of that e and bring down that exponent so I can solve for it. Natural log both sides. Gives me negative 0.0066890232 t equals the natural log of 45 over 110. And then I'm going to divide by negative 0.0066890232 on both sides. And I end up getting t to be equal to natural log of 45 divided by 110 divided by negative 0.0066890232, and I end up getting, double check me on this, 133.62457444 watt. Time is measured in watt because you picked it. Minutes. So this is time, so this will be in minutes. Here's my problem. WebWork wants this answer in hours. What are you going to do? Do you have to go back and redo the entire problem to put the time in terms of hours? No. All you got to do is convert this number. How do I convert 133.62 whatever minutes into hours? What am I going to do? Divide by 60, because there's 60 minutes in an hour. And when I divide by 60, this is just a hint, divide by 60, I end up getting 2.22707624 hours is how many hours it would take the bird to actually cool down to be that central temperature to be 110 degrees. Does that make sense? The temperature is moving towards room temperature. Now I picked another problem on here because there's some, the last little bit is in terms of interest and stuff, but I just handed you guys another problem of Newton's law of cooling. Why? Because we've got time to do it. So we might as well. Because I wanted to get you guys excited about math and science and why you guys chose to be, you know, science majors, engineering, math, chemistry, physics, biology, computer science, so forth and so on that we have in here. Why is this stuff so important? What is the big deal behind all this stuff? Well, here's a somewhat real world kind of a problem. Okay? Now, But I wanted to get into forensics. People get excited about watching CSI on TV and Bones and a few other these TV shows and stuff like that. You know, there's some real math behind what they do. You know, usually they don't solve the crime within, 2 hours or less, or 1 hour or less, whatever the television show is. But the reality is there is some major science behind what they do in terms of the forensics and things. And here's a great example of that. Now, Newton's law of cooling. What Sir Isaac Newton came up with, the actual physical mathematics, is this. Quote, this is his Newton's law of cooling law. The rate of change of temperature with respect to time is proportional to the difference between the temperature of the object and the temperature of its surrounding temperature. So what we're saying here is the rate of change, which means derivative of the temperature of the object with respect to time, is proportional to, means it's equal to some constant K times the temperature of the object, which is a variable T, minus the surrounding temperature, TS. Okay? Now, when we get you guys in differential equations, and we solve this differential equation thing here, we're going to end up getting the formula that we just played with. That's solving the differential equation. We'll teach you this later after we get you through calculus 2. Now, the other part of this problem is, trying to make this interesting here, is real world problems. I went back and looked at the files and stuff like that and pulled out the actual facts of the case of the O.J. Simpson, which I'm sure still people remember, even though you guys were no doubt small, if not born yet. All right, so here's the deal. O.J. Simpson was married to this lady called Nicole Brown Simpson, and they were divorced, and she was murdered with a friend of hers, Ron Goldman, who was somebody she met at the dinner, a restaurant or whatever, and it was a big bloody mess. And the police got there and found this lady sitting there, lying there literally, and with her head almost cut off, and they recognized who she was, they being the police. So what's the first thing police are supposed to do? We talked about this yesterday, day before yesterday. What's the first thing? Rule 1, rookie cops, everybody knows this. What's the first thing when a police officer runs across a crime scene, gets called into, hey, something's going on around here? What's the first thing to do? First off is they cordon off the area for making sure the evidence is secure, and they call in the detectives, and they're supposed to call the coroner so they can measure to try to figure out when the time of death is. So if you've got an alibi, does your alibi work with the time of death or not work with the time of death, that type thing here, because they're now collecting evidence. Well, the police didn't do that in this case. They had their suspect from day one, and they just all hopped into a big old car and ran over to O.J. Simpson's house and basically scaled over the wall and went after him to try to find him. But he had already left to go to, I think, Chicago at the time or something like that. So he wasn't even there. But this quote-unquote rush to judgment. So I made up a problem. So if they, the police did not do their job. They didn't call the coroner until 7 o'clock the next morning. The body was found literally at 12:30, if I remember my facts correctly here. The body wasn't found until 12:30 that night. So the murder must have happened relatively earlier than that, because they had seen her at a restaurant at 9 o'clock in the evening and stuff. And now she's murdered, and they found her body at 12:30. So sometime between the two is when the murder happened. But that being the case, the police did not call the coroner. They didn't do their job. They had their suspect, and they went after him hook, line, and sinker. And they didn't call the coroner until, 9:30, 7 o'clock the next day, and the coroner actually shows up at 7:30. The problem with that is bodies will move towards room temperature. This room is outside, okay? But between, 9 o'clock to 12:30, yeah, there may have been a little change in temperature, but not that much. But between, literally 12:30 and 7:30 the next morning, there's a lot of temperature change, because, when's the coldest time of the night? When's the coldest time of night? You guys know? Usually about 5 a.m., just before the sun rises, is actually because you've been away from the sun for the longest time, around 5 a.m. But then, what happens around 6 o'clock? Sun rises, and what does the sun tend to do? Heat up things. So now the bodies are now falling down towards the evening temperature of, I don't know, 60-some degrees that night, because this was in June, I think it was. And then they start going up towards, because now they're trying to follow, the sun is warming up the outside, so now the body temperature is going to start heating up. The mathematics is all gone, because once you got that dip, you cannot project back to the time of death, because it messes up all your math and stuff. So then they had to do stomach content and try to figure out the time of death by how much their food had dissolved in their stomachs, because they know what time they eat dinner and stuff like that. I mean, great forensics type stuff here. It doesn't work real well. What the coroner came up with, they died sometime between 9 p.m. and 12:30 p.m. Yeah, that's brilliant. She was seen at a restaurant at 9, and yeah, they found the body at 12:30. I could have figured out that math, and I didn't get paid anything for that. So it really wasn't that great of science. And with that missing information, it was an interesting case, because and honestly, the police really messed this thing up. I mean, blame the police on they didn't do their job. They got protocols and they didn't follow. But so I made up some information. So if they had called the coroner, so here we go. So I tried to give you some information about that. They were found dead at 12:30 a.m. on June the 12th. The coroner should have been called immediately and would have arrived sometime later. However, Los Angeles Police Department rushed to judgment, suspected O.J. Simpson to come, and forgot to call the coroner. Whatever. Until the next morning, approximately 7:30, the coroner arrived at the crime scene. Okay. This meant the temperatures of the bodies of Nicole Brown Simpson and Ron Goldman were coming close to outside temperature, and finding the time of death would be impossible using Newton's law of cooling because of that dip. Now they're warming up. You can't go back down and then warm back up again and be able to project back to the time of death. You got to get it on the downward trend or the upward trend, depending on if you're heating up or cooling down. But once you go over the hump, mathematically, it's impossible. Okay, so, all right. So if the coroner called immediately, all right, so here we go. The coroner should have been called immediately and would have arrived sometime later. And a big if there, so here comes my problem. So I just made up some data here. And if the coroner had been called immediately, the coroner would have found the bodies outside in the front yard where the outside temperature was 70 degrees. So there's my first piece of information. The surrounding temperature is 70 degrees Fahrenheit. Okay? And here's my Newton's law of cooling problem, and there's my 70 degrees Fahrenheit putting into my formula here. Okay? At 1 a.m., the coroner would have found the body, the temperature of Nicole's body to be 98.6. Now here we go. This is going to be the math. So I'm trying to give you guys information. Right at 1 a.m., just to make the math time easy for you guys, that's when the coroner first took the body temperature. So this is what I'm going to call time equals 0, and the temperature of the body at that first body was 89.6 degrees Fahrenheit. Does that make sense? It's 1 a.m., but that's when they first started measuring the body temperature. So I'm going to call that time 0, and time 0 is 89.6. Okay? 1 hour later, they would have remeasured the bodies and found it to be 86.9. So this would be at 2 a.m. This is now 1 hour later. The temperature 1 hour later is 86.9 degrees Fahrenheit. Okay. Now, from this information here, we should be able to find the time of death. And here's the amazing thing. From a math perspective, they didn't just have one body to kind of project back to. They actually had two bodies, so they clearly would have been murdered pretty close to the same time. So you could have used one body versus the other body and get two different math equations and see where they all match up at, and actually get an even better time of death from a science perspective and stuff. Now, don't get me wrong, I understand this is all gory and stuff like that, but this is real world math that's actually used. Your job, find the time of death. Let's see if we can find it. All right, here we go. We have our equation. Big T of little t is equal to C e to the kt plus 70, the surrounding temperature. The first thing you use is the initial temperature. That's going to help me figure out what that big C is. So, temperature at time 0 is equal to C e to the k times 0 plus 70, and that's equal to 89.6. K times 0 is 0, and e to the 0 is 1, gives me the equation C plus 70 equals 89.6. Subtract 70 from both sides, so C is equal to, what is that? 89.6 minus 70 is what, 19.6? Okay? So big T of little c equals C, which is now 19.6 e to the KT plus 70. You'll always use the initial temperature first. That allows you to solve for C. Question?
If C is just equal to the initial temperature minus the surrounding temperature,
Yeah.
do you even have to split the equation like that? Or?
No, you don't. You can actually go and straight use that one if you want to. I'm just showing you the classic math of why it always works. So you're right. You can just say, which is 89.6, the initial temperature minus the surrounding temperature. You get the same C every time. It works every time. All right. But now you actually have to plug in the secondary temperature. That's why they have to take two body temperatures. Now here's a gory thing. How do they take a body temperature of a dead body? How does the coroner do that? You guys know? Well, maybe they don't have a head. How are you going to stick a thermometer in somebody who doesn't have a head?
So they use like a really deep needle that's really thick and it has to go through the stomach or something like that.
Close. The liver, actually.
Liver.
The reason why. So now here comes for my biology majors out here. All right, here we go. They don't stick it under the tongue. The person is dead and may not have a tongue. I don't know. It's a bad situation here. But to measure the body temperature, they go after the liver. Why the liver? Because it's an internal organ, most internal organ that's surrounded by all the other organs, so it's insulated. And so they, like you said, will make an incision and stick the thermometer into the cavity, into the liver, and take the measurement of the liver is what they do. Again, it's because it has been surrounded, so it has a lot of insulation in it, so it's a good organ to actually measure the temperature, and it's also thick and dense and stuff like that. So it's a good organ to actually take a temperature off. That's actually how they do it. So, and then that was done 1 hour later. So T of 1 is equal to 19.6 e to the k times 1 plus 70 equals 86 or 86.9. Solving for k, I'm going to subtract 70. That gives me 19.6 e to the k times 1 is k, equals, this cancels, 86.9 minus 70 is what, 16.9. Agreed? I'm going to divide by 19.6 on both sides. So e to the k is equal to 16.9 divided by 19.6. Now to solve for k, what do I have to do? Take natural log both sides. So k is equal to the natural log of 16.9 divided by 19.6. Natural log of 16.9 divided by 19.6. Natural log of 16.9 divided by 19.6 is, and what's happening to the body temperature? The body temperatures are going down because remember the surrounding temperature is 70 degrees, so I'm expecting to be negative. I got a negative 0.1482159,443, which means the body temperature modeling formula, big T of little t is equal to, what is it? 19.6 e to the k negative 0.1482159,443 plus 70. And I will dot that in there a little bit. This is, like I said, the modeling equation. Now here's the question. The question is, when was the murder committed? We want to know the time of death. When was the murder committed? Well, when were they murdered? You got to do the math. Well, let's think about this. They were alive, assuming healthy body temperature. What's healthy body temperature? 98.6 degrees. So what I'm going to do here is I'm going to put the temperature as 98.6 degrees and find or solve for T, right? Find T. And I'm expecting T to be negative because I know at time equals 0 is 1 a.m. They're dead at 1 a.m. They must have been alive before that. So I'm expecting negative time, and then we've got to do the conversion of negative time, subtracting time from 1 a.m. Does that make sense? So here we go. So I'm going to get 19.6 e to the negative 0.1482159443 t plus 70 equals 98.6, and I'm going to go solve for t. Does that make sense? How would I solve for t? Subtract 70 from both sides. That gives me 19.6 e to the negative 0.1482159443 t equals, let's see here, 70 minus 89.6 is what? 28.6. Now what am I going to do? I'm going to move down here so I actually have more room. I'm going to divide by 19.6. That gives me e to the negative 0.1482159,443 t is equal to 28.6 divided by 19.6. I divided both sides by 19.6. Now what am I going to do? What kills off that e? Take natural log both sides, and I'm now trying to save some space here. Natural log of both sides, so this cancels. And now what am I going to do to solve for t? I'm going to divide both sides by 0.1482 here. So I get t equals the natural log of 28.6 divided by 19.6 divided by negative 0.1482159,443. And I end up getting, let's see what you get here. Natural log of 28.6 divided by 19.6. Divided by that, it gives me, I got t to be equal to negative 2.549504059 hours. Okay. Great. Still doesn't answer the question. Now, we've got to tell the police officers we're playing the coroner here. When was the time of death committed? Approximately what? Well, it's negative means it's 2.5 hours before. When did we start measuring this thing? 1 a.m. All right, so let's do the math. It's 1 a.m. I got to subtract 2 hours. 1 a.m. to 12, that's 1 hour. From 12 to 11, right? 11 p.m. now. You with me? And now I got to subtract off 0.549 of an hour. But this is a fraction of an hour. A fraction of an hour we like to convert to what? Minutes. So we're talking about 11 p.m. minus, and I'm going to convert the decimal now, and that decimal part right here is the negative 0.549504059. This is an hour. I'm going to multiply it by 60 to convert hours to minutes. Does that make sense? How many minutes is that? 32. Let's round it off to be 33 minutes. You with me? Minus 33 minutes. What is 11 p.m. minus 33 minutes? 10:27 p.m. That's what we got to be the approximate time of death. Could O.J. Simpson have done it? Oh, Lord, yes. We all know he did. But, okay, so, and I made the math, so yeah, I made him look very guilty because the reality of it was there was a guy that showed up at his house because he got a limo to the airport, you know, the rich people here. They got a limo to the airport, and the limo driver arrived at 11 o'clock. And the limo had to bang on the door, and he was, OJ's was scrambling around to get all his stuff together. He said he fell asleep or whatever. Got in the limo at 10 minutes after 11 or something like that. So he was witnessed at 10 minutes after 11 and stuff. So, but could he have committed a crime? Oh yeah, clearly when the crime was committed at 10:27. Does that make sense? Huh? There you go. But my point to this exercise is this, that this is real world science math. Now, honestly, do the coroners actually go back and do differential equations back in their office? Oh, no, they got computers to do this. But they have to input this information because we programmed all the mathematics into computers for the coroners and stuff like that. So that's, but you got to have two initial conditions on that type of stuff. All right, let's move on to interest rate stuff now. More formulas you got to know. All right. Well, as you know, we're science majors in here, but the reality is, even if we're science majors, we're all STEM majors in here, the fact of the matter is we're also all business majors. At the end of the day, you got to be financially knowledgeable. You know, whether you are an engineer, but you still could be running a company, you still got to know about finances and stuff. And one of these finances is about compound interest and about interest. What exactly is interest? What is the definition of interest?
The price of letting someone borrow your money.
It depends on which side of the fence you live on. Now, you're right if you're going to let someone borrow your money, but maybe you are the borrower, and therefore it's the interest rate at which you borrow money or the interest rate at which you invest money. Two different kinds of the sides of the fence here. Same idea, but if you go to the bank right now and borrow money, like you need a new car, what interest rate are you getting on a new car right now? Anybody know? Anybody bought a new car recently? Around 6 to 7%, depending on how good your credit rating is and stuff like that. You can get an interest rate for about 6%. Ain't too bad at all. But if you're investing money in the bank right now, you know what kind of interest rate you're getting at your bank? Not even 1%. It's about 0.5%. It's pretty sad. We had better rates in World War II. I mean, so investing money, not so good in terms of investing in the bank. Borrowing money is still good, but notice the difference. Let's just round it off. 1% for investing your money, 6% for borrowing the money. The difference is 5%. Who gets to keep that? The bank. That's how they're earning money for the bank and stuff like that. So now, the idea of compound interest is interest earned on top of interest. See, for example, in my bank, State Employees Credit Union, I get a monthly statement every month. You probably do too. And at the end of every month, what little money I got, the bank is going to give me some interest on top of the money that I've invested in their bank, and I will earn some interest. And next month, I will earn even more interest because of the interest on top of the interest that I had in the bank before. So the more times you compound, the more times they put money into your account, the more times when you do the compound interest, the better off you like it. I get it monthly, so every month. So the second month, I'll earn interest on what I made on that first month. And the third month, I'll make interest on what I made on the second month and third month. So the more times I compound. So you can go in extremes on this thing. So this is what we call the regular compound interest formula. A equals P times 1 plus R over N raised to the NT. Yes, you have to memorize it. It's calculus. We memorize everything. P stands for principal, or the initial value, principal, what you're investing. R is your interest rate. And remember, percentages are for people who can't do math. So if you got a 1% bank account here, what you really got is 0.01. You got to move the decimal over 2 places to the left, and you put the decimal version in this thing. It's a formula. N is the number of times a year you compound. So if I compound monthly, what would N be equal to? 12. If I compounded quarterly, N would be what? 4. If I compounded daily, N would be 365. If I compounded weekly, what would it be? 52. Number of times a year you compound. Number of times a year they put money into my account. And T is typically measured in time in years. And A is your future value, or the amount of money you're going to get out of the account. Okay? Now, so hopefully you'll watch the awesome pre-section video, because I did these two problems for you guys here. And so I want to do these particular problems. Now, here's the deal. I told you guys that when you're doing your investment on money, the more times they compound, the better off you like it. Well, okay, great. So in other words, compounding annually. Annually is N equals what? How many times a year is annually? 1. Compounded quarterly, N was equal to 4. Compounded monthly, N was equal to 12. If I compounded daily, N was equal to 365. But if I take that to an extreme, if I said compounded hourly, how many times a year is that? So it's 365 days in a year times how many hours in a day? 24. That would be 8,760. That was what N would be. Compounded hourly. And remember, the more times they compound, the better off I like it, because I like people putting money in my account. I don't know about you guys, but I like it when somebody puts money into my account. Usually, my parents, but yeah, whatever. But, all right. So, 8,760 times a year. But wait, keep going. Minutely. Every minute, I want the bank thinking about me and putting money in my account. So how many times a year is that? That'll be 525,600 times. Not good enough for me. I want every second. Every second, I want the bank thinking about me, putting money in my account, and making me happy about that. So how many times a year if I compounded secondly? 31,536,000 times a year. Now let's talk nanoseconds. I want the bank just living for me, loving me, and putting money in my account all the time. When you take this to an extreme, this is a limit. This formula turns into the classic formula that you've seen before, which is your famous PERT formula. This is called compounded continuously. This is continuous interest, and that's really what we're going here. That A equals P e to the RT. Same variables. P is the principal, amount of money you invest. R is your interest rate. T is time, but E is that 2.718 number that shows up in science naturally. So let's do problem number 8 here, since I did 6 and 7 on the old pre-section videos for you guys. All right, so here we go. If $8,000 is invested at 9% interest, find the value of the investment at the end of 5 years if it is compounded annually. All right, first off, your P is principal, $8,000. My interest rate, this is WebWork. You can even see the different font on this thing. I stole it, copy, paste this off WebWork. So, because if you guys know of an account paying 9% interest, let me know about it. I can guarantee an A in this class for you if you can show me this account. But it's a side point. All right, so interest rate is 9%. Like you said, the bank's offering 1%. Not even that. It's actually 0.5%. 1% of the state employees credit union only if you invest in their money market account type thing here. I mean, rates are actually quite low for you investing in the bank. You got to actually put in the stock market to make anything these days. And keep going. At the end of 5 years, so time equals 5. If we compound it annually, how many times a year is annually? 1. N equals 1. Here's my formula. A equals P times 1 plus R over N raised to the NT. A equals 8,000 times 1 plus 0.09 divided by 1 raised to the 1 times 5. So this is 8,000 times 1 plus 0.09 divided by 1 raised to the 1 times 5. And I end up getting, at the end of 5 years, I get $12,308.99. We'll round to the penny when we're actually dealing with money. Does that make sense? But now, I want you to see the difference if we use the same information and we now compound quarterly and what it does to my money. Compounded quarterly, how many times a year, what's N equal to if you compound quarterly? 4. So A is equal to 8,000 times 1 plus 0.09 divided by 4 raised to the 4 times 5. So I'm just going to recall down my formula and just change all those 1s to 4s. $12,484.07. How much interest did I earn by changing it from compounding annually, 1 time a year, to compounding quarterly, 4 times a year? How much extra money did I earn on $8,000? $176. I went from 12,308 to 12,484. Does that make sense? I got 170 extra bucks in my pocket here. I'm trying to teach you guys something. Does this make sense? Oh, let's go better. Compounded monthly. N equals 12. 12 times a year. So A would be equal to 8,000 times 1 plus 0.09 divided by 12 raised to the 12 times 5. So change these 4s to 12s. Put it up here, you guys can see it a little better. There we go. I got $12,525.45, rounding it to the nearest penny. So I earned another $30, right? $31. And if I compound it continuously, when you hear the word continuously, we change the formula to the famous PERT formula, where P, my principal, is $8,000. E raised to the interest rate 0.09 raised to your time is 12. This would be the best type of compounding a bank can offer. Okay? And which is, show you guys, 8,000. E raised to the 0.09 times 5 is $12,546.50. I earned another $20 on this thing, $21 and some change there. Does that make sense? Now, the reality is this. If you're investing $8,000, now don't get me wrong, $8,000 is a lot of money for most of us. $8,000 bucks. But if you're investing $8,000 to the bank, you're small potatoes. Okay, that's what most people invest. So you're going to be dictated to from the bank. Okay, and so the bank's going to give you whatever they want to give you, like your 1% at compounded monthly or compounded quarterly or whatever the bank happens to do for you. But here's the deal. This is what I'm showing you guys on the business end. Our goal for you guys is to eventually, hopefully, you'll not just make lots of money with your college degree and do very well and be very successful. Hopefully, you'll actually run the company at some time in your life. And if you're now running the company, you need to know about this, because companies also have money to invest. They want to sit there and put their profits aside and stuff like that because they got some other projects and planned or whatever the case may be. So instead of $8,000, let's talk about $8 million or $80 million that you've gotten to invest in the bank. Once you're talking those kind of money, you dictate to the bank. The bank doesn't dictate to you. You go to the bank with your, this is the interest rate I want, this is how I want it. And which way do we want it? If we're investing the money, which one gives us more money? Compounded continuously. I want these people thinking about me all the time. I want them putting money in my account all the time, because compounded continuously, I'm going to earn the best amount of money. Because here you're looking at it, well, yeah, between compounded annually to compounded continuously, I earned an extra $240. Okay, that's $240. Yeah, that's a lot of money at $8,000. But if we're talking about $80 million, that's what, $240,000. That's a couple people's salary, 2 or 3, probably 3 people's salary in your company, that all you did was dick around with the paperwork and tell the bank exactly how they wanted it, and they just paid for 3 employees for you, and you don't have to worry about it. Does that make sense? Did I lose you guys anywhere? This is why this stuff is real important, and you need to know about it. All right. Let's move to section 3.5. Section 3.5 is about trig functions. Now, I know you've seen this before because it's a requirement to graduate high school these days. It's trigonometry and the unit circle. And hopefully you've got at least the first quadrant of the unit circle memorized, because from that you can project it over, because you need to know about this unit circle. These are exact values. Whether 30 degrees or in radians, your pi 6, 45 degrees, pi 4, 30 degrees, pi thirds, 9 degrees, pi halves. And remember, here's how the unit circle works. The x-coordinate of the point is equal to the cosine of the angle, and the y-coordinate is equal to the sine of the angle. And if you need it, if you take the y-coordinate divided by the x-coordinate, that's the same thing as the sine over cosine, also known as the tangent of the angle. Okay? So, how do I use the unit circle? If I ask you what is the cosine of pi thirds, you go to pi thirds. Cosine is the x-coordinate. I look at the point x-coordinate, it's 1/2. So therefore, bless you, the cosine of pi thirds is 1/2. Does that make sense? If I come over here and go, okay, what is the sine of 5 pi fourths? I go to 5 pi fourths. Sine is the y-coordinate. So the sine would be negative square root of 2 over 2. Okay? And here's the deal. If you know everything in the first quadrant, all you got to do is project it over. In your second quadrant, the only difference between the second quadrant is it's negative, positive on the points. Third quadrant is negative, negative. And the fourth quadrant is positive negative. So it's the same points, whether it's pi thirds or 2 pi thirds, because it's straight across. The points are the same, 1/2 square root of 3 over 2, but in the second quadrant, the x coordinates are all negative. Third quadrant, both the x and y are negative, and the fourth quadrant, just the y's are negative. This is, quote unquote, how you use the unit circle stuff. We also have a big old chart down here for every angle between 0 and 2 pi of the exact value type. Sine, cosine, tangent, cotangent, secant, and cosecant. Remember, cosecant is 1 over sine. Secant is 1 over cosine. Cotangent is 1 over tangent, or cosine over sine. Tangent is sine over cosine. So with doing these ratios, these are the numbers that you end up getting. But that's not what this section's about. This section is about inverse trig. Okay? So, let me come over here and get myself a nice clean sheet of paper here. Let's first focus on sine and cosine. Sine and cosine. If I graph y equals the sine of x and y equals the cosine of x. Let's take a look at this. Sine goes 0, pi, excuse me, pi halves, pi, 3 pi halves, and 2 pi. And it bounces between 1 and -1. You with me? The sine of 0 is 0. The sine of pi halves is 1. The sine of pi is 0. The sine of 3 pi halves is -1. The sine of 2 pi is back to 0. And I know you've seen him before. He's the famous sine function. It waves. Starts at the origin, then goes up, back down, and back again. The cosine function, 0, pi halves, pi, 3 pi halves, 2 pi bounces between 1 and -1. But the cosine of pi is 0. Cosine of 0 is 1, excuse me. Cosine of pi halves is 0. Cosine of pi is -1. The cosine of 3 pi halves is 0. Cosine of 2 pi is back to 1. You get this wave. And of course, it extends on. These guys extend on. Okay? When we were doing inverse trig functions, because that's what I'm really after. I'm really after discussing what the sine inverse is and what the cosine inverse. Now, the sine of an angle equals the y coordinate. Sine of x equals y. When you do the sine inverse, it's the sine inverse of a number, and the goal is to get the angle back again. So you take the cosine inverse of a number to get the angle back again. If I actually do this one, it'll be the sine inverse of y equals x, and the cosine inverse of y equals x. If y equals the sine of x, then sine inverse of y equals x. And if y equals the cosine of x, cosine inverse of y equals x. Also, to let you know, doing inverses, if you're doing computer programming and stuff, you've got to go back to the Greek. Sine inverse is also known as the arc sine of y equals x, and the arc cosine of y equals x. The arc cosine is the cosine inverse. But here's what I'm trying to tell you. When we were doing inverses, way back when in the beginning of chapter 3, as part of the review stuff that you guys are supposed to know how to do, and it's on your next test, how to find an inverse function. What's your step 1 on finding an inverse function? What's the first thing you got to do? No, it was the second step. Switch x and y was the second step. You had to first make sure it was what? 1 to 1. What is 1 to 1? It means you have to have a graph 1x equals 1y. How did you check for 1 to 1-ness? The horizontal line test. Knock yourself out. These things fail the horizontal line test. These are not 1-to-1 functions. And because of that, to create the inverse functions, we have to make them 1-to-1. So we make them 1-to-1 by doing this. We do what we call a restricted domain. Now, if I only focus on between negative pi halves and pi halves of the sine function, just in this little box, is it 1-to-1? Any horizontal line will only intersect the graph at once. But if I extend it outside, these things are doubling back on me and it's not 1-to-1. So we have to have a restricted domain. So when I'm talking about the sine inverse of a number equals an angle, the number, equals the angle there. Excuse me. The angles, the angles have to be between negative pi halves and positive pi halves. This is the restriction. You have to look between negative pi halves and positive pi halves. Okay? For cosine inverse, I got the same problem. But to make it 1 to 1, I'm going to block it off here at 0 and come over here to pi. This little section. So the cosine inverse of some number equals the angle. The angles that you'll get back are going to have to be between 0 and pi. And you don't worry about outside. So this is actually 1 to 1. So what we got here is we have what we call the restricted domains. And there's 2 restricted domains with this stuff. Which means, let me break it up for you. When you look at this stuff, when you look at angles between negative pi halves and pi halves, there are 3 trig functions that use this restricted inverse, this restricted domain. That is the sine inverse of a number equals an angle, the tangent inverse of a number equals the angle, and the cosecant inverse, which is 1 over sine, of a number equals the angle. These 3 inverse trig functions use the restricted domain between negative pi halves and pi halves. The restricted domain of 0 is less than or equal to theta, which is less than or equal to pi. This is used by the cosine inverse of a number equals an angle, the cotangent inverse of a number equals an angle, and the secant inverse of a number, remember secant is 1 over cosine, of a number equals an angle. These 3 trig inverse functions use the restricted domain of 0 to pi. Which means, when I come over here, and I'm looking at this unit circle from the restricted domain perspective, okay? Well, let me just draw it on. I hate to mess up my beautiful picture here. All right. Here is my unit circle. You with me? Sine inverse of a number equals an angle. Tangent inverse of a number gives you the angle back. And cosecant inverse of a number equals an angle. You've got to use the angles between negative pi halves and positive pi halves, which means this. This is pi 6, this is pi 4ths, this is pi 3rds, this is pi halves. This is the point square root of 3 over 2, 1/2. This is the point square root of 2 over 2, square root of 2 over 2. This is the point 1/2, square root of 3 over 2. This is the point 0, 1. This is the point, this is 0, 1, 0. But there's 3 angles in every quadrant. To link the first quadrant to the negative, to the 4th quadrant, you've got to be a negative angle. This is negative pi 6. This is negative pi 4ths. This is negative pi 3rds. This would be the point square root of 3 over 2, negative 1/2. This will be square root of 2 over 2, negative square root of 2 over 2. This is going to be 1/2, negative square root of 3 over 2, and this is the point 0, negative 1. These are the only points you get to use. So what I'm talking about here is this. Down here when I'm doing inverse trig, we don't do 11 pi 6. You call this guy negative pi 6. You see that 7 pi 4ths? You don't call him 7 pi 4ths if you need an inverse function in this particular quadrant. You've got to use negative pi 4ths. You don't use 5 pi 3rds, you use negative pi 3rds. You don't use 3 pi halves, you use negative pi halves. These are the angles when you need this restricted quadrant. And if I'm dealing with cosine inverse, cotangent inverse of a number equals the angle, of a number equals the angle, and the secant inverse of a number equals the angle. 0, pi halves to pi. You use the top half of the unit circle. You use these guys. Notice one thing. There's one quadrant when I'm doing inverse trig I never use, and that's the 4th quadrant. It's because it's going to violate the one-to-one policy. Does that make sense? So, knowing that fine fact, let's answer these questions. Now, I did a bunch of these problems on the video here. I'll answer just a couple of them before I move on. Let's do this one. What's the cosine inverse of a half? Cosine inverse of a half. And typically, I want my stuff in radians unless I tell you otherwise. Okay? Cosine inverse uses the top half of the unit circle. So where's cosine's the x-coordinate? Where's the x-coordinate a half? It's at what angle? Pi thirds. Remember, with inverse trig functions, the answer is the angle back again. So what is the cosine inverse of negative square root of 2 over 2? Again, cosine inverse works the top half of the unit circle. Where is the top half? Got an x-coordinate of negative square root of 2 over 2. What angle? It is 3 pi fourths. Does that make sense? What is the exact value of the sine inverse of 1/2? Sine inverse uses the right half of the unit circle. Okay? Let me blow this thing down. You guys see a little bit better here. There we go. So the sine inverse uses the right half. Where is the right half? The sine is the y-coordinate. Where is the y-coordinate equal to a half at? It's at pi 6. What's the sine inverse of negative square root of 3 over 2? Sine inverse uses the right half of the unit circle. Square root of 3 over 2 for the y-coordinate is down here. But don't tell me it's 5 pi thirds. That's wrong. What would we have used the negative angle? So what would that be? Negative pi thirds. It's this angle down here. Does that make sense? You can't use the positive angles. You've got to rewrite the fourth quadrant as negative angles. What about the tangent inverse of square root of 3? Well, remember, the tangent inverse of y over x is equal to my angle. So I'm going to have to rewrite this, and I'm going to be thinking about unit circle stuff. When I see a square root of 3, I'm looking at a square root of 3 over 2 1/2 ratio. Does that make sense? And so that would be the square root of 3 over 2 divided by 1/2. And remember, this is the tangent is y over x. This is the y-coordinate, this is the x-coordinate. And you got to give me the angle back again. Well, since this guy is positive, they're both going to be positive. And the square root of 3 over 2 is on top, and that's the y-coordinate. X is going to be 1/2. Tangent inverse uses the right half. Where is the y-coordinate? Square root of 3 over 2. Where is the x-coordinate? 1/2. What is the angle? Pi thirds. But you have to rewrite that square root of 3 to be able to see it in the unit circle world. What about the exact value of the tangent inverse of 1? Well, that would be the tangent inverse of 1. The ratio has to be the same to get 1. So if I'm using just this right half of the graph, the y over x has to be 1, which means the points have to be the same. And the only 2 points are going to be the same as the famous square root of 2 over 2 square root of 2 over 2 angle, which means the angle, what's the tangent inverse of 1 going to be? It's got to be right half, but it's positive, so it would be pi fourths. If I said negative 1, then one of these guys would be negative, and it would be the y-coordinate being negative because I got to be over here, and it would have been negative pi fourths is your answer. This is how you use the unit circle stuff. Last two that I actually did on the video is this. You got to know, hopefully you remember what the graph of y equals the tangent of x looks like. Do you remember the y equals the tangent of x graph looks like? It bounces between negative pi halves and positive pi halves. And at negative pi halves and positive pi halves, these are vertical asymptotes, and you get a squiggle. This is the famous tangent graph, right? And as I take the tangent, take the limit, as x approaches pi halves from slightly below of the function, if I'm slightly below pi halves, my function is blowing up. If I'm going up, I'm going towards infinity. Does that make sense? Which means that I can reverse this and say that the limit as x approaches infinity of the tangent inverse of x would be pi halves. So the tangent, if you take the limit as x approaches infinity of the tangent inverse of x, you get pi halves, you get the vertical asymptote. And if you take the limit as x approaches negative infinity, what angle do you think negative infinity is going to be at? Being negative infinity is down here. It would be negative pi halves. Does that make sense? So, review of these guys. But I will get to next time because I'm running out of time here. But that's all right. I'm exactly on my syllabus schedule right here. Look at what's coming next. What we were just discussing are these inverse trig functions. There's 6 of them. Sine inverse of x, cosine inverse of x, tangent inverse of x, cotangent inverse of x, secant inverse of x, and cosecant inverse of x. But I taught you guys something last time, and that was this. This is right out of the textbook. But for every rule they give you out of the textbook, there are actually 2 rules. There's the basic rule you got to have memorized, and there's going to be a chain rule version of that rule. We'll go over that next time. Study hard. I'll see you guys on Thursday. Thank you.